Good morning, everyone. In this video, I'm going to talk about the LR circuit, or sometimes we call it an RL circuit. The L stands for the inductor, and R is for the resistor. So where inductor and resistors are connected together in a circuit here. So let's start with the circuit here. So we have the circuit here where our resistors and inductors are connected in series, and this is the source, and we have a switch here. So when the switch is open, there is no current passing through the circuit. And now if we now let's say time equals to 0, we close the circuit here, or we close the switch here. So as soon as we close the switch, there will be a current in the circuit. But now there is another term or another component, that is the inductor, and this inductor hates to changes. Initially the current was 0, so if there is any current coming in the circuit, it will like to oppose. Because it is opposing, then in order to get the maximum current in the circuit, it takes a certain amount of time. The current does not grow immediately. It takes a certain amount of time to reach to its peak value. Okay, because this inductor hates the changes. If the current is increasing, it would like to behave in a way to decrease the current. Or if the current is decreasing, then it will produce an induced current to increase the current here. So in this case, the moment we turn on the switch, there will be a current. So the induced EMF across this inductor will be in such a way that the induced current will be opposite, because it hates to changes. The current is increasing, so the induced current will be in a direction opposite to the direction of the original current here. Okay, so in order to have the induced current in this direction, this term must be positive and this terminal must be negative. Only in this case we'll get the induced current in this way here. All right. Okay, so now let's calculate mathematically how long does it take to get the current to its peak value, or what will be the current after a certain time. That's what we're going to calculate. We're going to use a Kirchhoff's law, the Kirchhoff's voltage law. And in order to use the Kirchhoff's law, you might have already studied that we have to make a loop here. So let us consider here, this is the loop here. I'm going to change a different color. And this loop direction, it can be clockwise or anti-clockwise. Is entirely up to you. All right. So here we have closed the switches. The moment we close the switches, the time starts. So what is the Kirchhoff's voltage law tell you? That the Kirchhoff's voltage law tells you that in a closed loop, which is this loop here, the total voltage must be exactly equal to 0. So let's start here. So we have a battery, and again, if the loop is going from negative to positive terminal, then this EMF or this voltage must be positive. So we have this one as a positive. And the other term, we have the current here, the voltage across the resistor. So if the current direction and the loop direction are parallel, then it must be negative. And what is the voltage drop across the resistor? I times R. I times R, and this must be negative because the current and the loop direction are parallel. And now how about this inductor here? For the inductor, the inductor also behaves as a battery. So you can think of this as a battery with this positive terminal and this is a negative terminal, and the loop is going this way. If the loop is going from positive to negative, then it must be negative. That's the reason we have negative. And we have chosen at this one as a magnitude only, and the reason is, and I will tell you the reason, because we already have identified the polarity of this induced EMF, or this terminal must be positive and this must be the negative. Okay, so that's the Kirchhoff's law. Okay, so if you recall the Faraday's law, what is the Faraday's law tell you? Or from the mutual inductance or the self-inductance, in fact, the induced EMF across the inductor is given by negative L di over dt. Okay, di over dt, and in this case di over dt is positive, so this as a whole will be the negative. And if this is negative, then that's how it has to be the polarity of the sign. It will be opposite to the original source. Okay, so if you have any questions, write down in the comment section below, because these are the important steps when you solve mathematically. So make sure that you understand, you convince yourself this is the right approach. All right, so here now I'm taking the time derivative of this equation here. So this is simply dE or dE epsilon over dt. The r is a constant, but I is not constant, I is changing. So di over dt, and this is the induced EMF across the inductor divided by the time. This is equal to 0. And this one is the source. So the source does not change with respect to the time. So this term must be exactly equal to 0. R and di over dt, if I look at this term here, di over dt, I get epsilon L, that the induced EMF divided by the inductance, self-inductance. That's what I get here. And this term as it is. And now I have rearranged these terms, the induced EMF terms all one side, and R, L, and time on the other side. Okay, it's easy to follow. And now once I have these terms, my goal is to solve for the induced EMF value as a function of time. But this one is derivative, so I must integrate this term. So once I integrate, this is the term I get. Whenever you have integration, it does have limits. So initially, at the time equals to 0, the induced EMF was epsilon 0. That's the maximum value. And at any time, this is the value here. And the time this is equal to 0, and we start from the 0 time. At any point, this is the time here. So initially, again I'm telling you, the initial at time equals to 0, the EMF induced across the inductor was the maximum value, and this is at any time. And if you do this math, if you follow this math step by step, this is the equation you will get here. Okay, so if you take a time derivative of epsilon or EL, then let me write down the equation here. Dx over x, the integration of this one is ln x. Okay, and ln x and ln and exponential are the inverse function. So I have applied that one and solved the magnitude of the induced EMF. And you see here E0, that is the power, the original EMF, that is, or that is the for the battery here. This is epsilon 0, and R L over T. So as a whole, this term has no units. So what does this mean? That means this term must be the reciprocal of a time, and we call this one tau as an L over R, and this is called as time constant. Okay, so I have rearranged, or I have wrote this equation in this form here. Epsilon 0 E over negative T over tau here, and the tau here is L over R, which we call as a time constant here, the time constant. So there is a physical meaning, the meaning of this time constant here. And again, one more time, what is this term means? This is the induced EMF across the inductor at any point. E0 is the battery, the voltage, and this tau is the time constant. This is L over R. Okay, so if you want to rewrite, because this is the magnitude, if you want to rewrite this one in a more appropriate form, I can rewrite this equation this way here with a negative sign here. And the reason for this one is this negative sign simply indicates which end of the inductor will be positive and which end will be the negative. So we already have done these things here, but again, by the Lenz's law, the moment we close the switch, the current starts increasing. This inductor hates the changes, so the induced EMF will be in this direction. And as the induced EMF is in this direction, this term must be positive and this term must be negative. So whenever you think about the direction of the current, do not think about going this way. You have to go from one terminal to the other terminal in this way here. Okay, not directly across, from this way to this way. So that is the direction of the induced current, and this direction of induced current is always trying to oppose. If it is increasing, then it will be this way, it will oppose the changes. Okay, so that's the equation we got here. Now what is the meaning of this time, the constant here? So let's explain this meaning here. Before explaining, also let's find out the current. How do you calculate the current here? The current in this circuit here. So the current, how do you find out the current? The current we get by the voltage divided by the R, and this voltage here is the total voltage here. So if we look at the net voltage, this one, and this also acts as a battery to some extent here. So the net EMF, because this one has the is in the opposite way, the net voltage will be epsilon 0 minus epsilon L divided by the R. That is the current. Okay, or you can simply solve from here. You can simply solve from here, whatever works for you. If I solve for I, what would I get? I get E epsilon 0 minus epsilon L divided by R. Okay, that's the current I get. So I have this current equation, and all I'm doing here is plugging the value of this induced EMF value, which I have here, right here, which I have right there. This is the magnitude, so this is the right here. So I'm simply plugging this value here, and then I'm taking out the like terms here to one side, and this is the E0 over R, or this is the potential difference of the battery, and divided by R, which is the initial current I0 of I0 here. Now, so if you have to understand this equation here. So I0 here is at the time equals to 0. Okay, that's that at the time equals to the I0 means the maximum current in the circuit here. Now let's try to understand these things one more time here. So at time equals to 0, when you simply close the switch at that time, that is the time equals to 0, this one will oppose, or this one will have the maximum resistance, or it will have the maximum the strength to oppose. So that means at that point the potential difference across this inductor will be exactly as the battery, so there will be no current in the circuit. So that's what I get here. At time equals to 0, if I simply plug in, then it will be I0 1 minus e to the negative 0. If this is e negative 0, so that means this term is 1, so the current will be 1 minus 1 will be 0. So there will be no current in the circuit. If there is no current in the circuit, that means it behaves as an open circuit. So that means inductor simply behaves as an open switch here. And after a long time, here I'm calling mathematically infinite time. So if I plug in let's do that here. If I plug in time equals to infinite, 1 minus e to the negative infinite, so this term will be 0. So that we will have the maximum current in the circuit. So this maximum current is not at the time equals to 0, but after a long period of time. Then you might be wondering, what is the long period of time? So it depends upon the time constant value. Sometimes 1 second, in most of the situation, the 1 second, 2 second is the infinite time, a long period of time, because usually this value, the tau value, will be in microsecond or sometimes in millisecond. So 1 second, 2 second, or let's say 5 second is the infinite time here. Okay, so the current, so when we look over here, so when you have this kind of circuit, the moment we close the switch, the current is not a maximum. It takes a certain amount of time to reach to its maximum value, because this inductor has the maximum resistance initially, then this strength goes slowly and slowly, and then finally there will be the maximum value of the current. That's what exactly the meaning of this one is here. Okay, so the two important things: at the time equals to 0, the current in the circuit is 0, and that means it behaves as an open circuit because there is no current. And after a long period of time, the current in the circuit will be the peak value I0. That means the inductor behaves as a short circuit. So what does this mean again here? Let me go back to the circuit one more time. After a long time, this inductor will simply behave as a wire with a zero resistance. And if it simply behaves as a zero resistance, what will be the current? The current will be the E0 over R. Okay, so at the time t equals to 0, it behaves as an open circuit, open switch, and at time equals to infinite, or after a long period of time, this simply behaves as a short circuit or simply as a wire. All right, so now if you look at the voltage across the inductor and the current across the inductor, that's how it looks like. So as the time passes by, the current starts increasing. This is an exponential growth here. Okay, and the time constant means how long does it take to reach to the 67% of its maximum value, that we call as a time constant. And if you look at the induced EMF across the inductor, it starts going down, it decays exponentially. And for that one, the time constant we define as how long does it take for the inductor to have its value as a 37% of its the maximum value, that we call as a time constant. And why do we have the two different kinds of graph here? The one is decreasing exponentially and the other is growing, and the reason is here. If you look at this equation here, just pay attention to this equation here, these two equations here. So this one has e to the negative t over t, that means it is decaying, and here we have 1 minus e over t over t, that means it will be slowly growing. Okay, so now the one more thing, if we have the two different inductors, now let's say just for a comparison, L1 and L2, if you have higher L2, that means it will take more time to reach to its peak value, and if you have a smaller inductance, then it will reach out to its maximum value quickly. And if you have no inductor at all, then the current will reach out to its maximum value immediately, because there is no any resist, there is no any opposition by the inductor. So the stronger the value of the L will be, the longer it will take to reach to its maximum current. So this is it from this video here, and if you have any questions, write down in the comment section below. Thank you very much.